So it should be recording now. My name is Alex Forrest. I know many of you, and many of you I don't know. So I'm the current Comms 2020 president, and I want to welcome you today to the 35th annual Comms conference, and perhaps our oddest conference to date. So this is our first foray into virtual conferences. And so we're trying it this time instead of a one-day meet like we've typically done in the past. What we're doing is a series of webinars throughout the week. And so we're going to start off today with Alicia Cortes, who I'll introduce shortly. And then we'll go through the week, and then on Friday, what we're going to have is we're going to have a town hall panel discussion, and then also some presentations from sponsors and from our students and from our student awardees who are doing great research around the state and across our district. So as a bit of an introduction to this particular conference, we're certainly in an era where there's a lot of distractions for all of us. And when I say distractions, I mean there's a lot of major things happening in the world, and whether or not it's wildfires or a pandemic or social unrest or the upcoming election, there's a lot going on out there that makes it very challenging to continue to do the research and work that we all do to protect the water in our system. So basically, whether or not it's mercury contamination or HABs or anoxia or aquatic evasives or any of the great areas that all of us work in, these are things that we still need to continue pushing forward. And this is sort of one of the core things of comms, and one of the things I've been really impressed with is this idea of our sort of core mission to protect and sustainably manage and advance research in the area of freshwater lakes and reservoirs. And so this is a major priority. So the more that we can continue to facilitate this in this era where I'm sure we are all tired of looking at Zoom meetings and trying to coordinate remotely and trying to do the work that we've all done historically and continue to do it in the same excellence that we've done before, I think it's essential. So coming up with innovative ways to continue to work together and continue to network and facilitate those networks, I think is a critical aspect. And so part of that is getting knowledge out there. And this is something that we've continued to do through this whole era. We've done a series of webinars throughout the past year that have been very well attended. And we'll continue to do these webinars, both now during this week of our virtual conference, but then also going forward. Also, we as an organization stress the importance of students. And so we continue to fund, typically before we've funded students to come present at the conference and sort of help give them a forum to talk about their research. And we're continuing to do that and continuing to grow that. These also lead to great talks and basically having discussions and forums to discuss ideas is important. And then it's going to lead to this town hall on Friday, along with a social hour at the end of Friday. So for those of you that can attend, pick and choose what you want to come to throughout the week. We don't want anybody to get too saturated and want to get turned off of it, but we will have some fun activities at the end as well. So with that sort of kicks off the 2020 conference, and hopefully next year we'll be able to do it in person. And our keynote speaker for today is Alicia Cortes. And so Alicia is a friend and colleague of mine at UC Davis. who is going to be talking about the impacts of climate change, and particularly about the impacts of climate change on Clear Lake. She originally did her master's work in one of her masters in England before going to the University of Granada and doing a master's and Ph.D. there in environmental fluid mechanics. So she does a lot of work was in Mediterranean lakes and reservoirs and rivers, and looking at how rivers would transport basically loadings into lake systems. And then she came out after that and was down at UC Santa Barbara for about 5 years, where she has worked in a broad variety of different lakes around the world, and everything from Arctic lakes and looking at winter limnology, where she and I have collaborated together on before, to tropical lakes down in the Amazon basin, to lake systems in between. And so we were lucky enough to get her on board the UC Davis team to be working up in Clear Lake with us. And so she has done some already amazing work up there and continues to sort of push that forward. And she's interested in hydrodynamic modeling and applying numerical models to lake systems, from 1D models, 2D models, simplified models, 3D hydrodynamic models, coupling that with observations of systems in terms of harmful algal blooms, to nutrient transport, to chemical transport. So we're really lucky to sort of have her as part of the team at UC Davis, but we're also lucky to have her today to give this talk. So with that, I'm going to let Alicia take it from here and take it away. And I'll shut down my own video. But one point of logistics, if you could keep your video off, and then if you have questions, we'll have a Q&A period at the end. If you could post your question into the chat, and Mark, Silos, and I will be monitoring the chat and sort of making sure that we ask the questions. So we'll be your mouthpiece for Alicia at the end. All right, so with that, I'll shut myself off.
Alrighty, so let me get this started and I will share my screen. So please, I would like you to tell me if at this point you can see my presentation on presentation mode. Can you see it?
It looks good.
Great. Well, so first of all, thank you very much, Alex, for the introduction. That was really flattering, and well, you said too many things, so at some point I didn't realize that I've done so much, so thank you for that. And also thank you very much for the invitation, for being a key speaker today. I'm very, very excited to meet the CALMS community today, even if it's virtually. And hopefully, as Alex said, one day in the very near future, we will all meet in person. So looking forward to it. But just let's get started with this work, as Alice also said, that I'm going to present today about predicting hypoxia in Clear Lake. That it's been the work that many people have been working on during the past year. So first of all, and before diving into details, as you can see in this first slide, I'm not alone. So this is not work that I have done by myself. We have a big team behind. And here you can see that this presentation that I'm gonna present today is just the result of very hard work from several co-PIs from the Tahoe Environmental Research Center. And I'm sure that probably some of you know Jeff Schlado, Steve Sadro, and of course, Alex, who is here with us today. But also we have a huge team of researchers and grad students behind us. Some of them are listed here, such as Drew Stang, Mika Swam, Nick Franston, Ruth Thierkill, and Samantha Sharp, among many others. So by the end, I will take some time to thank you all of them. But I didn't want to start this without making sure that you knew that this is a lot of work for many people. So just after this quick introduction, I will dive in to the main topic. And I would like to start the presentation just providing a quick overview of hypoxia in water bodies. So first of all, as many of you know, dissolved oxygen, from here on, by the way, I will say DO just for the sake of brevity. So anytime that I say DO, that means dissolved oxygen, is essential for pretty much having a very healthy ecosystem and many processes which are occurring in the ecosystem. And the DO is tightly related to temperature distribution in the water column. So that's why here I'm gonna show you as a cartoon typical profiles of temperature in the water column on the left and DO on the right on a typical shallow lake that here I just decide that is gonna be 15 meters deep. And I'm gonna show you profiles during 2 different seasons, just to explain you how these two variables are changing over time. So first, during winter, we have normally profiles which are showing that the water column is fully mixed, which means that the temperature is uniform top to bottom, as you can see here with this blue line. And at the same time, DO concentrations are also uniform and high. And I pick this value of 10 milligrams per liter, which is normally a reasonably high value for aquatic ecosystems. And then when the time goes on and the summer and the spring arrives, what we normally see is that there are temperature gradients in the water column, as you can see here with this red line that I'm showing you in the left, on the left side of this diagram. And these temperature gradients that the temperature water column presents is what we normally call a stratification. And this stratification, what it does is preventing the exchange between the shallow waters and the deep waters, which means that probably the surface waters are gonna get oxygenated because they're in contact with the atmosphere, but the deep waters, they have pretty much a barrier and they cannot get reoxygenated because respiration and other biogeochemical processes are occurring. So what it happens is that the high values of DO, they get drawn down, and then we don't have that much DO anymore in the bottom water columns. And that's what we are gonna call hypoxia. So pretty much I wanted to make sure that everyone understand what I mean by hypoxia in this presentation. And unfortunately, this depletion of DO in water bodies, it's been one of the main challenges of water managers during the past century. So definitely it's a topic that needs quite a little bit of attention from all of us who would really love a healthy aquatic ecosystem. So first of all, and also just providing a little bit of background, I would like to review why, well, pretty much why all this hypoxia is happening, the effects and the causes and effects of this hypoxia, just to provide a little bit of overview and make sure that everyone understands what is causing hypoxia and what are the consequences of these processes. So here, and just to do that, I'm using again another cartoon to make sure that everyone gets the main concepts really clear. So here in the left, you can see an oxic water body. And on the right, you can see what I call an anoxic water body. And all the cartoons are trying to introduce you these causes and effects of hypoxia. So the main causes of DO depletion are excessive nutrient loading, for that it's what we call eutrophication, normally due to human activities such as agriculture, farming, or industry, and pretty much discharge from many sources like human sources. And also because of changes in climate. As Alice mentioned, this presentation is going to have some focus on climate change. So I would like to make sure that, to let you know that hypoxia is because these changes in climate, which are mostly reducing the mixing in the water body and increasing these temperature gradients that I mentioned at the beginning. And as a result, these causes of hypoxia are causing also impacts on the water body. And here in this cartoon, I'm showing you some of them, which are, for example, the increasing harmful alga blooms, also reducing the fish habitat. Here you can see that we go from a healthy fish ecosystem from a dead fish ecosystem. So the one on the left, sorry, the one on the right is the one that we don't want. And another effect of hypoxia is the nutrient release from the sediments. So that's also going to be one of the topics of this week. So just stay tuned and you will hear more about it. And pretty much all these negative consequences, as you can see, is not fun for the system to have all of these effects. So you can imagine that there have been many attempts to try to predict this drawdown in lakes and reservoirs, because that's something that we don't want for the ecosystem. And just as an example, and pretty much because it's recent, and I found, as Alex mentioned, really cool the fact that they have developed a numerical model. Here, I would like to show you the case of the Great Lakes Environmental Research Laboratory, who have developed an hypoxia forecast tool for Lake Erie using a 3D model. And hopefully maybe we'll have something very similar for Clear Lake in the near future, but not yet. And in this animation on the left, I would like to show you the forecast change of the two variables that we are studying. So in the top, you can see the temperature at the bottom of the system, and on the bottom, you can see dissolved oxygen also at the bottom of this system. So again, temperature on the top, DO at the bottom, and here you can see that this animation is gonna go through summer starting in July until fall, ending sometime around February. So here, as I go through this animation, you can see that low levels of DO next to the sediments occur during the summer, and then the bottom water is reoxygenated when the water column mix. And you may say, well, why do you know that the water column mix if the water temperature is increasing? So I know that because if I play this again, here you see that the bottom waters are cold, so that means that there are gradients and the cold waters are staying down deep. And then as the water column mix, you see that the temperature is increasing is when we see the hypoxia disappearing. So you can see, well, this is super interesting, it's really informative, and if we have the right tools and the right model, this is just really powerful to predict hypoxia. But then I tell you the problem, and the problem is that these type of models require a lot of data, a lot of calibration, a lot of time, and as I'm saying, they are not really hard to set up, and pretty much that's something that probably some water managers, they cannot really devote time because it requires a lot of time. So this is promising, but it's not quite what maybe some people are looking for. So that's why my main goal today is presenting you a simple tool that is able to predict this drawdown of DO in lakes and reservoirs. And for that, I'm gonna show you a very simple 1D model, simplified from all these complex 3D models that require very few input variables and also very little calibration. And I will talk about that later on. So for that, and just to apply this 1D model, we have used a site study that probably some of you already know because you are from California, but for those who are not, we are going to be presenting data that we have collected in Clear Lake, which is located in the central range of Northern California in Lake County. So here you can see a map of California, and this is the location of Clear Lake. So there are multiple reasons why we have picked this system, this beautiful system, by the way, for this study. Some of Clear Lake's singularities are that it's the largest natural lake in California. So remember, part of Tahoe is in Nevada, so Clear Lake is the largest, with a surface area of 151 kilometers square. is the oldest lake in Northern California, so it's been around us for a while, is one of the top contributors to the local Lake County economy through boating and bass fishing and other interesting activities. Is naturally eutrophic, so it has a high level of nutrients and is biologically very diverse and sustain a very broad community of aquatic and also terrestrial species. And most importantly, it's essential for cultural activities and economies of Native American tribes. And here, just for the sake of listing, I'm listing some of them. As you can see, there are many Pomo communities and also Elem Indian colony and the Khoi Nation of Northern California and some other that I didn't list, but definitely it's a territory that has many Native American tribes. And because of that, I would like to take some time at this presentation to thank all of them, because they allow us to work in their territory and mess around with Clear Lake a little bit. So thank you to all of you for letting us be in your territory and allowing us to collect some data. And hopefully all the work that we are doing is to provide some answers to the many questions that have been posed over the years. So yeah, thank you very much for providing us access and also letting us be around there. Thank you. And Clear Lake, it's a very unique lake, as I'm saying, but also it has many environmental challenges, and that's why probably some of you have heard about it. And some of these environmental challenges are eutrophication, as probably you have heard over the years because of intensive agriculture, which are releasing a lot of nutrients into the lake. Also cyanobacteria blooms, which may release toxins that compromise the water quality of the system. Extreme wildfires, as we were talking before starting this conference, that's something that it's happening very often lately. And here you have a photo from the 2018 Mendocino Complex fire, and I'm sure that very soon we will have one from the recent fires that happened the last month. So that's something that Clear Lake is suffering too often. Also, it suffers from mercury contamination due to the proximity to the abandoned sulfur-bound mercury mine, pesticide overuse, and fish kills due to many reasons, but one of them, low levels of DO. So all these challenges have led to the creation of a 15-member Blue Ribbon Committee for the Rehabilitation in Clear Lake that it was created in 2017. And I would like just to mention that this is a great community who is working really hard to try to come up with a set of recommendations to rehabilitate the lake. And here you can see that there are many people involved. So again, tribes are very important, and they are a very important part of this committee that I mentioned, that it was created in 2017. There are members from Lake County with expertise in agriculture, economy, environmental and public water supplies, members from UC Davis, and also from Central Valley Regional Water Quality Control Board. And here, for those who may be interested in checking what we are doing in this committee, you can see a reference to the website where we post all the meetings summaries and all the work that we have been doing. So you will have access to some of the stuff that UC Davis is presenting, and also Lake County and some other people who are proposing recommendations to make sure that Clear Lake tries to improve its quality. This task that the Blue Ribbon Committee has right now is not a simple one, because as you can imagine from all the characteristics that I gave you before for Clear Lake, this lake is not simple. It's a complex system, and also is challenging from the point of view of the physics. That is, as Alice mentioned before, one of the things that I've been more focused on lately. So Clear Lake, just as a quick overview, is a very large lake. And as you can see here on the map that I have in this slide on the top left corner, it has multiple basins, which means that some of the conditions that we measure at one point may be completely different in a different part. So it's not a simple lake where you go and measure in one side and then you know what's happening. Definitely the fact that it's a multi-basin system complicates things. It's a shallow lake with no more than 50 meters, which means that a large fraction of water is exposed to the sediments, which take us back to the internal loading concept that I mentioned before. And lastly is a polymictic lake. And for those who haven't heard this word before, polymictic lake means that a lake has multiple mixing events through a year. And that means that if the lake mixes and stratifies, then we are going to have cycles of oxygenation and hypoxia through the whole year. So just to provide a picture of what a polymictic lake means, here I would like to show you a counterplot that shows the time series diagram of lake temperatures measured in Clear Lake that we measure at the deepest site that we monitor in the lake. And this time depth diagram shows you these temperatures between March 2019 and February 2020. And here on this diagram, you can see that I have time on the x-axis, depth on the y-axis, and these colors are representing temperature. Here you see the scale and the color bar on the right. And also these dots that I have on the left are representing the thermistors where we have that we have in the water column measuring temperature over time. And this black line at the bottom is showing you how the water level was changing over time. So initially when we start our sampling, we have a fairly deep water column and you can see how the water column shrink over time. So again, from 2019 to 2020. And also you can see from these colors that the temperature in Clear Lake changes quite a lot. So we go from 28, 27 degrees during the summer to around 10 degrees or even less, 8 degrees during the winter. So 10 degrees temperature difference is quite broad, which means that we can go through a broad variety of processes happening through the year. And also, again, just coming back to the beginning and to the diagram that I showed you at the beginning, here and mark here with these white dash boxes that you see in this plot, I would like to mark the periods when the temperature has the temperature is changing in depth. So again, if there are temperature gradients in the water column, that means that there is a stratification. And that happened very clearly 3 times during spring, summer 2019 in May, June, and early August. And at a different time, you can see that the temperature was uniform through the water column. And that you can see because the temperature is uniform through the water column. So again, here is an example of stratification and mixing through a whole year in a polymictic lake. And when we align these temperature measurements with the measurements that we did of dissolved oxygen that I have here in the bottom panel, you can see very interesting things. So again, just for you to get used to what I'm showing you here in the bottom panel, I'm showing again another time depth diagram. And in this case, the DO measurements are the result of 3 loggers, 3 DO loggers that we place at 3 different heights about the bottom. And again, you can see that we are focusing on what is happening with the oxygen very close to the sediments. And it's very interesting to observe how quickly the oxygen got consumed at this location close to the sediments, as you can see by this red color, at the times when we have a strong stratification. So again, you can see here the same as we saw three big stratification events. We also had three big anoxic events in 2019. And also around here, you can see that those were not the only ones when we have low DO. During the fall, there were also other mild events in which the DO was low in the water column. So looking at all this data, we wonder, well, how can we link this temperature stratification with the hypoxia that we observe in the lake? And one of the answers that we came up with is just using a predictive tool that is based on how much the lake heats and cools due to the different processes that I'm showing you here again on the cartoon on the left. So some of these processes are solar radiation, input of energy, condensation, evaporation, or the effect of the wind on the water body. So pretty much our idea was, is there any relation using this gain of heat or loss of heat that actually let us predict hypoxia? And more specifically, and just for give you an idea of the type of data that our model needs, these are the meteorological conditions that we use for the example that I'm going to present you today. Here in these different panels, I'm showing you variables that we measure at Clear Lake using one of the meteorological stations that we have around the lake. And as you see, we measure input or incoming solar radiation on the top panel, surface water temperature on the lake, air temperature, relative humidity, and wind speed. And just to provide also some comments about this data, and for those who are interested, I can go on and on and on with this, but just for the sake of brevity, I will say that this meteorological data has also some seasonal patterns, the same as the temperature on the lake, where you can see that the incoming solar radiation was high during spring and summer, and it went down in the fall, and it was minimum during the winter. And that's tightly related with the surface temperature, that it did pretty much the same, high during the summer, low during the winter, the same as with the air temperature. But in this case, you can see that the oscillations from day to day are larger. By the way, these values are daily. And also notice that the surface temperature didn't experiment such as large swings in temperature as the air temperature. And the relative humidity had also this seasonal pattern, but in this case, the relative humidity was low during the summer and high during the winter. So it was very nice to get these patterns recorded. And for the winds, it was harder to come up with a nice pattern for all the sites, because pretty much the winds have more like a daily pattern. But still, you can see that there are definitely fronts of high winds with periods of calmer conditions. And I can say that the winter is probably not the windiest, and the spring can be one of the windiest periods in Clear Lake. So this is our input data for our model. And here, as I mentioned, is just an example of how to use, or what are the outputs of this predictive tool that we are suggesting. In the top panel, I'm showing you the DO time series that we measure close to the sediments. So if you remember from the 3 loggers that we had in the water column, here I'm just showing you the concentrations that the bottom one was recording. And in the bottom panel here, so again, this is lake data that we measure. And here, this parameter of this time series that I'm showing you in the bottom panel is an energy term that we compute using the meteorological conditions that I just showed you. So I would like to highlight with this two-plot figure that it's very interesting, the fact that we were able to predict with this energy term that we calculated when the hypoxia started and how long this period of hypoxia actually lasts. And just to get a little bit into the weeds of what our method actually looks like, I will give you some details of the method. So again, I'm going to go through this slide probably too quickly. So if anyone has questions by the end of the presentation, please feel free to ask any further clarifications, but I would like to show you how this simple method works, because it's definitely a neat idea. So now I would like to just firstly say that we name our method and we call it Winkler method to predict anoxia. And you may wonder, well, where are these names coming from? So for those limnologists in the audience, you may recall that this is pioneering, these names are the surnames or of some pioneering researchers on heat budget and also on dissolved oxygen measurements. So Edward Birch was a very important name for heat budgets on lakes, and Lajos Winkler did also very important measurements of DO in water bodies, in inland water bodies. So that's why we are using these two names to call our method, the Birch-Winkler method, or as I will say from here on, the BIW. So here, what I'm showing in this diagram that I have on the left are pretty much the three variables that we use for our model to come up with our predictions. So on the top panel, I'm showing you the DO concentrations next to the sediments. And again, this is something that we are going to use for only a very brief period of our model, which is the calibration. But once that we have the model calibrated, we don't need DO concentration. Okay, so for this calibration, we have DO next to the sediments. Then we have an energy term that is the net surface heat flux. So pretty much this is representing the amount of heat that the lake gains and loses according to the meteorological forcing. And the bottom panel is our BIW energy term, which is just the cumulative net surface heat flux between two consecutive hypoxic events. So just to provide an overview of how these calibration processes goes, I will just enumerate a set of steps in order just to come up with a very robust prediction. So first, what we need to do is to define a DO threshold of hypoxia. That is what I call here DO THR, and is marked here on the top panel with a green horizontal dash line. So once that we know this value, we can define the beginning of our hypoxic event, because below this threshold is when we define that the system is hypoxic. And once that we have this beginning of the hypoxic event, what we do is to calculate our VIW term as a sum of the net surface heat flux over the period between two consecutive hypoxic events. Okay, so then we come up with a cumulative value of these net surface heat flux at the beginning of the hypoxic event that we are going to call BIW1. Okay, so again, coming from the top, we need to define a threshold, once that we define a threshold of DO, we have a way to define the first day of the hypoxic event, and then we can define a value that of the VIW term at the beginning of the hypoxic event. And then what we do is to reset to 0 the VIW term, as you can see that I'm doing here. And the next step is defining when the Hypoxanidan is finishing. And for that, what we look at is when the VIW actually drops very suddenly. And that's when we define the T2 time, the end of the hypoxic event. As a result, the length of this hypoxic event is just the difference between T2 and T1. So again, just for a recap of this model calibration, we need DO next to the sediments, just to give an idea, just to know what's happening in the system. We need meteorological conditions to compute the net surface heat flux and see how much heat the system is gaining or losing. And we need to calculate this VIW term that we are introducing in this model, that it's a way to calculate the cumulative energy that the system is gaining between two consecutive hypoxic events. And then all the lines that I'm adding here to define the beginning and end is just a way of defining this VIW1, which is going to be unique for each system. And again, once that we have this VIW value at the beginning of the hypoxic event for a specific water body, we don't need DO concentrations next to the sediments anymore. And we will be able to predict when hypoxic events start and how long they last, just based on the meteorological conditions that we know that the system have. And we can also predict over time. So we found that this tool, using some simple information, it's a very interesting tool to use as a warning tool for water purveyors, also for cyanobacteria sampling or oxygenation systems. So that's the reason why we would like you to try this tool, because we have done an application in Clear Lake, but what happens in other lakes? That's why we think that if some of you are interested in predicting hypoxia in your system, let's get together and talk and try these calculations in your system. And here, just as an example, we think that probably some lakes, which are also shallow, in California could benefit from this tool. As an example, we think that Lake Elsinore in Southern California, and also Lake Anza and Lake Contra Loma, Reservoir Contra Loma, also in Northern California, could benefit because some of these systems have been suffering for very bad harmful algal blooms lately. So we think that predicting hypoxia could be beneficial to maintain their water quality. And again, if you're interested in using this tool, which I hope that it would be of benefit for many of you, this is the list of parameters and time series that we will need in order to apply this method. The parameters that we need are lake latitude, lake elevation or atmospheric pressure, wind sensor height, and the maximum lake depth. And the early time series, again, early is the frequency that we had from Clear Lake, but I'm also interested in checking what happened if we probably use only daily values. So again, early is the first request, but if you have other frequency, we can work around that. But the type of information that I would need to run this model is lake surface temperature, air temperature, relative humidity, incoming shortwave radiation, wind speed, and as I mentioned, DO next to the sediments, but only for the calibration. So once that we calibrate the model and get this VIW1 parameter calculated, we can just run with the predictions. And before I mentioned that we would like to apply that to shallow lakes, but why not to deeper lakes, right? So here you have a photo of Shasta Reservoir, and I'm looking forward to the time when we can apply this model to this reservoir to see if it actually works. And we speculate that the application of this method to this deeper systems will show fewer hypoxic events than in shallow lakes due to the lower daily rates of DO consumption next to the sediments, and also the system will need to gain more energy in order to experience these hypoxic events. So definitely, probably there are a few things that we need to modify in our model, but probably not that many, because it's mostly based on the energy gain and lose in the system. So we are very optimistic, and we are hoping that this tool will also work. And just as a final part of this presentation, I would like to spend some time, let me see, yeah, I have time for that. So I would like to spend some time talking about the many applications that this tool could have. And some of these applications, well, pretty much all of the work that I'm going to present right now, it's been work that it's been led for grad students in our department who have been working extremely high to get very interesting results. And as an example, oxygen depletion is essential for oxygen depletion is also a problem for fish habitat. So that was one of the interests of Drew Stan, one of our master students. And here, what Drew found out is summarizing this two plot figure that I have here on this slide. And here, what I'm showing you is the distribution of DO in the top panel during 3 days over the summer, and also the fish biomass on the bottom panel here over the same period of time and through the same depths that we measure with an echo sounder. And the key observations from these two plots is that during the low oxygenated period, that it was also the strongly stratified period, the fish move to the shallow depths, as you can see with this white line that is showing you the mean depth where most of the fish was located. But these poor fish had to live in shallow waters in the summer during the stratified period. So as you can imagine, the poor fish was not very happy. While when the water column was mixed and fully oxygenated through the whole water column, the fish could stay at deep depths. And in that case, fish was mainly happy. So pretty much the take-home message that Drew was able to find in his research is that under hypoxic conditions, the fish are changing its vertical distribution. And he was able to quantify that using tools which haven't been presented in the past. So thank you very much, Drew, for this piece of research for Clear Lake. And also another reason why studying hypoxia is important is because under hypoxic conditions, nutrients from the sediments can be released. And that's what we call internal loading, as I mentioned earlier in the presentation. And that was the interest of Nick Franstead, also one of our master students. And what Nick did was, well, pretty much he led our laboratory experiments using sediment cores collected in Clear Lake, which have provided the first direct estimate of the annual load of soluble reactive phosphorus. So the input of phosphorus that is released from the sediment, which is actually readily available for phytoplankton, he was able to come up with an estimate of the annual value, and he found out the value around 25 metric tons per year, which represent between 30 and 40% of the soluble reactive phosphorus load into the lake. So this, as you see, as a result of the experiment is a fairly high number. But if I tell you that after repeating these experiments, this summer under warmer conditions, we are still checking values, but it's mostly likely that this 40% value could be even 60 when we did these experiments under warmer conditions. So that was work that is being done this summer. Nick and others in our department have been leading this experiment, and hopefully very soon I will be able to give you a more accurate number of how representative is the internal load in Clear Lake. So again, this is another piece of research led by one of our grad students, also very informative for this project. And as a final application for Clear Lake, oxygen is also relevant for cyanobacterial growth. And this is one of Samantha's interests. And she has conducted cyanobacteria measurements also using a broad variety of instrumentation, going from grab samples to radiometers, drones, or underwater vehicles. And one of her goals, among many others, because she has also other interests, was improving and validating available remote sensing tools from the San Francisco Estuary Institute to detect cyanobacteria in Clear Lake. So she has been working very hard on one manuscript that it's been submitted to a journal. So stay tuned, because hopefully very soon you will see paper describing this nice work that Samantha has been doing. And finally, you may wonder how climate change is going to affect the prediction of hypoxia with our 1D model. So sadly, in the last few years, we have observed many events which are really indicating that hypoxia is getting worse in Clear Lake and in other lakes around the world. So here as an example is the fish kill that happened in August 2017 in Clear Lake. And also more recently, this is a photo taken by Mika Swan this summer. So he went to Clear Lake just to do some regular monitoring and maintenance, and he found this awful view of Soda Bay, where you can see that the bacterial bloom was really peaking. So when we look at these events and these negative impacts, we wonder how is this going to change in the future. So according to our predictive tool, that again is based on energy terms, we believe that lakes and reservoir will be gaining more energy because most likely temperatures are increasing and more solar input is entering the system, which will lead to more hypoxic events. And also mixing conditions are mostly reducing. So we normally see less mixing events, which will probably lead to longer hypoxic periods. And with that, I think that I've been talking enough. So that's all that I have for today. But again, I don't want to finish this presentation without thanking a very, very big team of people who have been working super hard during the past year and even more during the last few months under the current COVID circumstances. There have been people who have been like really making this possible. So thank you to all of them. I really appreciate all the work that you do and all the time that you have invested, how professional you are. And well, pretty much thank you for making this possible. And thank you to all of you for listening today. And I will be happy to take any questions.
Well, thank you, Alicia, for a great presentation. We have a lot of questions here. So I'm going to start. Just a minute, find my cursor here. I'm going to start with actually Joe's question, because and then we'll sort of work our way from the top down. And at some point, if we go farther than 1:30, I will step off, and Mark Silos is my backup as the moderator, so he'll take over for questions then.
Okay.
So the first question is from Joe Sullivan, and I apologize. I know I didn't get Joe's name wrong, but if I say your name wrong, I apologize in advance. But his question is, it seems like a lot of work to create a model to predict hypoxic events when we already know a lake goes hypoxic. Why not just oxygenate? I'll glibly say I think that's showing his small lake bias, but I'd like to hear what you have to say on that one.
Well, again, I'm using the applications that I just showed at the end of the presentation to somehow show you that the critical period when we are actually having trouble in the system is the anoxic period. And again, as you just mentioned, Alex, we really have a really broad variety of systems. And if we look for the oxygenated period in a deep lake, that's mostly the whole time. So I really think that there are two reasons why we want to nail the anoxic period. First, because it's the one causing trouble, and second, because we want to make this the most general as possible. Does it answer your question? Yes.
Sarah, you got a thumbs up. Great.
Yep.
Okay. So next was a question that came through, Mark. What drives summertime de-stratification events at Clear Lake?
Still working on that, Mark. So mostly many people think that is wind, but I'm also can tell you that temperature and relative humidity play a role. So I don't have a definitive answer for that, but just for you to see again the meteorological conditions of the lake. Right, here you go. Nope. All right, so let me see if I find it. So I only want to mention that it's a very tight relation between air temperature, relative humidity, and wind. So the three factors play a role, and depending on how they combine, then the mixing occurs during the summer. So it can be because the wind went up, it's because the air temperatures went down for long enough period, and also the relative humidity, as you can see, oscillates and swings quite a lot during the summer. So those three factors are making the lake mix during the summer. Does it help?
Great. And then a related question from Dina: what time step do you use to predict how long hypoxic events last?
Again, the question?
What time step do you use to predict how long hypoxic events last?
Oh, daily.
Great. That's easy.
Yep.
And then one from Keith: how patchy is the hypoxia in Clear Lake? And do you have multiple BIW thresholds for different arms of the lake? Great question, Keith.
Yeah, and I love that one because that's part of the uncertainty of the model. So yeah, there are like a bunch of calculations that we've done. So just to give you an idea, I don't move fast enough between here and there. Here you go. Okay, so sure. So here, hopefully, Keith, you can see a table where I have different values of this BIW1 threshold for different arms and also for different DO thresholds. So you can see that even in Clear Lake, this BIW term is changing quite a lot. So definitely it's an uncertainty that we need to live with. But once that we identify that, once that we calibrate the model, it's something that we know depending on the DO threshold and the place where we are trying to predict hypoxia. Does it help? Yep. Great.
And a related question from Sarah Ryan: what is the DO threshold of hypoxia? And existing fish water quality standards are 5 ppm. And I think that last table you put up.
Yeah,
Uh,
that's right, Sarah. So just to show you again, because probably you didn't have time to check what it was in there. Yes, so here I have values of 1, 2, 3, and 4. And again, the value you were asking, the threshold of DO for fish, is something that varies depending on the study that we are checking. So this is again stuff that I've been learning from Drew Stang, and Drew informed me that 3 milligrams per liter is normally the threshold value, the theoretical, the textbook value. But then depending on the species, then you can go to very low values like 1 or 2 milligrams per liter when the fish is very strong and they can resist these low levels of DO. And if the fish is not so strong, then you need values as 4. And also these thresholds vary depending on other applications, as you can see here in the table. So we don't we didn't work with these numbers only for fish. We also took into account how these values change depending on internal loading. So yeah, pretty much it depends on the fish type and the type of application and the system. Does it help, Sarah?
Thank you. Yes.
Great.
okay, the next was from Stephen McCord. Lake Anza has a new oxygenation system operating now. Could the model simulate that DO addition and mixing effects on stratification too?
Not at this point. So I really haven't had that. So pretty much what the model is doing is using the meteorological conditions to see what the system should do according to that type of external forcing. So adding oxygenation is something interesting to add. So thank you for the comment. I really haven't thought about that.
And a follow-up question from Stephen as well. Rather than focusing on energy input, would it be better to use stratification strength?
But then how are you going to take into account? Well, I can tell you that we have tried that model and we use buoyancy frequency for that. And that model wasn't that hot. It was really good when the stratification strength was really high, but for periods where the stratification wasn't high, the model wasn't providing such a good value. So that's the case. So just very quickly, I will show you what I mean by that, and I'm happy to talk about it if you want. So I have a slide showing you that. 1 second. Stratification strength. Here you go. And now sharing again. And I want to share this one. All right, so this is just coming from a manuscript that we have submitted to Water Reserve Research. And here you can see that using a stratification strength, buoyancy frequency, we have measured DO as a black line, and the red line is showing the DO calculated using buoyancy frequency. And here I'm showing you estimates of DO for different basins in Clear Lake. But just if you want to have a look at this one, the bottom panel, which is in the lower arm, sorry, in the upper arm, which is the shallowest part of the lake, you can see that the predicted value, the red line, is not really quite predicting the really important hypoxic events. So it does such a good job sometimes with the oxygenation, but not with the hypoxia. So that's why I think that we need something a little bit more informative, because only the stratification strength may not be as good indicator of that. So we have tried and we haven't been lucky. That's my answer.
Great. And we're happy to chat about it more.
Yeah.
If you're curious to apply this somewhere.
Yep.
Brian Maddox has a question about whether or not you think this would work in lakes and reservoirs with an inflow and outflow.
So that would be another input energy. And the same as, sorry, I don't remember who asked about oxygenation. So the same as the oxygenation input would be another source of energy, the inflow will need to be added. So now I'm thinking that we need to come up at the end of the day with a way to modify the BIW term, that energy that the lake is gaining or losing. So the same as we need to add or subtract energy for the oxygenation system, the inflow will add or subtract energy. So that will be the way that I would suggest that the inflow will play a role. Does it help?
Yeah, that's great. Thanks.
Okay, now a question from Chandler Smith. You mentioned near the beginning of the presentation that you needed lots of data for your model. How often did you sample DO and temperature?
For Clear Lake, temperature is measured every 10 seconds. For DO, we have two different types of loggers. So we sample DO every 30 seconds when we have very high resolution sensors, which are from RVR, and every 10 minutes when we use PME sensors, the mini dots. So different. So it's quite high resolution.
Great. Next question from Yipeng. Is this model mostly a statistical model, or are there some process-based components? Can the 1D model incorporate effect from aeration, air, not oxygen, and mixing systems? And I think we've kind of answered part of this, but just wanted to talk about process-based components.
Okay, so the process base, well, coming back to the beginning of the question, he asked about the statistical models, right?
Is this model mostly a statistical model, or are there some process-based components?
It's mostly process-based because we just use, we quantify the processes which are causing heating and cooling in the system. So if we come back to the diagram that I show you here, where are you? Here you go. So this one, come back here, skin share, right. So pretty much we are just quantifying these processes using equations, which are using meteorological values. So process-based, that's my answer.
Great. Now we have one more question from Maya Singer. But if anybody else has more questions, keep posting them. And we'll keep reading them. So Maya's question is, where would you say the cutoff depth range is for shallow lakes versus deep lakes for the 1D modeling method that your team developed? In other words, at what depth do you think the 1D model would no longer work well?
That's a great question. And I haven't thought about it. So I assume that probably it has to be related, it should be related with the DO consumption from the sediments. So I assume that once that this value is not relevant anymore, I guess that it's probably not such a simple answer, because it also depends on how productive are the sediments, right? So you probably cannot say from 50 meters we are in deep systems now, because then the sediments can be different on a system that has 50-meter deep or maybe only 20 meters deep. So I don't know the answer to that. I don't want to give you a certain value, but I don't think that depth is the only factor that it's going to be affecting the fact of going from shallow lakes to deeper lakes. I believe that DO consumption from the sediments will also play a role.
As would residence time, I think, which addresses
as well.
One of the earlier questions
Inflow.
From Brian.
Yeah, that's a good one. Thank you for the comment.
Yeah, so I think that's it for the questions, unless anybody else has more. If nobody types anything in, I would comment, well, first of all, thank you very much for all the great questions, and to Alicia for the great talk.
Sure.
Like I said, we'll be posting both the questions and the talk itself up on the website, but give us a couple days before we get that done. And then also, if anybody's out there that's curious to try this method, I'm sure Alicia is searching for candidate lakes to try out the technique on, so that we can look at these various components of depth and residence time and oxygenation system. There's all these other components that are involved in this. I would also sort of conjecture that possibly attenuation coefficients, so will affect the heating of the water, etc., and the net primary productivity as well. So with that, thank you very much, and I encourage everyone to come tomorrow. So Brian Furman's going to be giving a talk at the same time, and about algal management. So I think it'll be another great talk. And that one will be co-hosted, I believe, by Eli. So unless there's any other questions, I'm going to end the recording there. Okay, so.